Very good afternoon to everyone. A warm welcome to our renowned guest, Professor Kairon Jian, my colleagues, and all participants. It is my pleasure to welcome you to the 5th International Conference on Innovation and Emerging Technologies 2025. It is also known as ICIT 2025. This conference is organized by the Faculty of Technology at the University of Srijawardhanapura in Sri Lanka. This is the 5th year of connecting researchers, innovators, and technologists. Our theme is exploring technologies for a smarter and sustainable future. Today on November the 26th, we are holding pre-conference workshops on various themes from different disciplines. I'm happy to moderate this session on energy conversion in solid oxide fuel cells. In this session, you will be introduced to the basic principles and energy conversion processes of solid oxide fuel cells. These fuel cells are expected to play a key role in future of clean energy production. So I am delighted to introduce our resource person, Professor Kairon Jian, from School of Material Science and Engineering, Sichuan University of Science and Engineering, Sichuan, China. Professor Jiang is also research fellow at the University of St. Andrews, UK. She worked there during the time when I was doing my PhD. She has also worked at Nanyang Technological University and Seoul National University as well. She received the Royal Society of Edinburgh Hutton Prize in Energy Conversion for her outstanding work. We are truly honored to have Professor Jiang with us today. She brings strong academic expertise and good experience in university-industry collaboration. She has also collaborated with our university as well, and we have published several papers on energy materials. This workshop will help you to understand how SOFC works, and you will learn about the energy conversion mechanisms, common materials, and recent developments in biogas and direct carbon fuel cells. Before we begin, I would like to inform you that all participants will receive an e-certificate for their attending this workshop. So please make sure you register during this session. You can either use registration link or QR code to register this session. The QR code will be shared during this session in the chat box. So please keep an eye on that chat box as well. Also, during the Q&A session, you may speak or drop your question to the chat box, and I will be glad to read them out to get further clarification. I am confident that this session will be highly informative and engaging. I wish you all a very fruitful and productive workshop experience. Without further ado, let me invite Professor Jian to begin this session. So everyone, please join me in warmly welcoming Professor Kairon Jian. Professor Jian, now the session.
Hello. Good afternoon for you all. I'm in the UK. It's morning now. Can you hear me? Anyone?
Yes, we can hear you.
Okay. Good afternoon.
We can't see your face properly. Can you put your? Can you go back?
Yeah.
Now it's better.
Yeah, it's better.
Yeah.
Okay. So, good afternoon, everyone. It's my pleasure to give this presentation. Thanks for Dr. Pentagade gave me this chance to give this talk. And it's really my first talk I did a presentation before, but it's also because of the problem of the internet and visa. So I've done an online one. So I hope the sound will be okay and you can hear me clearly. So I will just start my presentation. I'll start to share my screen with you. And it doesn't work if I select a window. Yes, allow. So I'll come to my presentation page. It's a bit challenging for me. Yeah, I hope you can see it. Can you? Can you see
yeah,
my slides now?
We can see your slides now.
Yeah?
Yes.
Okay. It's my great pleasure to give this presentation. So thank you for all the organizations. And so we've been able to share my ideas and research achievement over these years. So my talk today is energy conversion in solid oxide fuel cells. I'm Cairong Jiang. I'm from University of Science Engineering. So as my email address showing in there. So if anybody is interested on my research, and so just contact me with this email, or you can ask Dr. Pentagray to get my contact address. So my talk will include 6 parts. First is background of solid oxide fuel cells. I don't know how many you have been involved in this subject, but it's quite a wide subject, even it's only a solid oxide fuel cells. But there's a lot of material preparation and processing procedures and etc. So I will focus a bit on anode and cathode materials, and then move on to biogas fuel cells. And some of my research when I have done in University of St. Andrews, finally is acknowledgement. Sorry, my slide is yeah. I finished my PhD degree at the University of Science and Technology of China in 2007. So in the same year, I moved to Seoul National University to start my research fellow research. But for that 1 year, I've been focused on super capacitors, but mainly on the interface chemistry, and then spend a little time on Nanyang Technological University. I'm doing some software resistant anode. This is how I started with anode materials. Yeah, yes, I've done some materials, but mainly whole cells when I'm doing my PhD. But I started to more focus on sulfur resistant anode in 2008. So by 2009, I came to the University of St. Andrews. That's now I'm here. I'm coming for a year visiting at the university to focus on fuel cells. By 2017, I finished my research fellow and started my present position at the university, Sichuan University of Science and Technology. So my main research interests are mainly solid state ionics, electrochemistry, and energy conversion and storage materials. I started to collaborate with South Africa for the carbon utilization. So I focus on fuel cells part, and we feed in fact, this electrolysis cell. We feed the carbon monoxide and hydrogen and to the fuel cell facial tropics device to produce some oil and new energy. So my research is mainly just a few topics, and including all the energy conversion and some materials related to the anode, cathode, or some electrolyte, and interface chemistry if some chemical reactions are involved. And that I mentioned carbon dioxide utilization. We started from carbon dioxide and react with water to be electrolyzed into carbon monoxide and fuel, and to be used for the energy field, for preparing chemicals for industry. And the 5th part of energy devices. So I've been focused on a lot of energy devices assembly or preparation. Thank you for all the work of my student and also my husband. So we work together at Sichuan University of Science and Engineering. And this presentation I present here, some stuff is from the University of St. Andrews and some is from my present work. So thank you for all this, my students and the supervisors. I will start it from the background. So, the world energy consumption is increasing every year. Maybe 90% of fossil fuels is consumed year by year, including oil, natural gas, and coal. So we were thinking about how to make it better. Maybe we can concentrate on some work doing renewable energies. And these renewable energies can give more choices, like to reduce the carbon dioxide emission. So we have a target like zero emission by 2050. And now we got in 2004, and the reported value is 378 ppm, means it's a quite high level because we use a lot of fossil fuels after the Industrial Revolution. And maybe it's a time to find a solution now. And the problem of energy we're having now is we use more fuels, means we have less supply. And is this supply, all the resources, some of them are not friendly. So especially location-wise, and some of them is, if there's a lot of emission of carbon dioxide, it's not good to environmental we are living on the Earth. For the the whole reservation we have, resources we have, we can last for roughly 400 years, but what to do after 400 years? So we think maybe it's time to do something. And the first could be transport carbon dioxide or heat into deep oceans. Maybe this lasts 400 to 1,000 years, but we have to think about the generations afterwards, how to reduce the carbon dioxide buildup. Maybe we need to do some change because the carbon dioxide emission is quite high by now, and we use a lot of energy every day. Maybe there's a few choices that we can do. Maybe we have high reserves of solar energy. It's 600 tegawatts per practical, but how to use it? And solar energy could convert it into biomass. That's one of my subject. And another thing is, can its other fuels or other sources available for us to create more electric, like hydrogen and hydrogen carbon? But hydrogen fuel cells is one of the choice maybe we could use and to make a better solution. From the source of solar, it started from biomass, or we can store it into batteries here. And to make chemicals, another choice is could be we come from hydrogen, we get some pure hydrogen, and we use the materials of hydrides to make chemicals and to feed into fuel cells to provide energy. And another thing is hydrocarbon can be used for fuel, but mostly if we know for the fuel cells, we have a few types, and in the following slide, I will give you how many types of fuel cells we have, but mostly they only use hydrogen as fuel, and hydrogen carbon cannot be used as fuel in like proton exchange fuel cells. So this one of the choice could be fuel cells, and fuel cells give a few advantages, and the first one is high efficiency. High efficiency means it's 50 to 60%, like the graphic shown here. For traditional combustion engines, it gives 20 to 30% efficiency, but fuel cells can give more than 30 and 40, even 60. But if we combine with coal generation, it could be as high as 80 to 90%. The second advantage could be size independent, because depends on where the location is. We can build a bigger size or a smaller size. Some of them could be even a portable small ones. And another advantage could be the zero emissions as well. So it can operate on hydrogen or other fuels. This is how the fuel cells can bring us the solution. One of the cell type, if we think about the fuel we use, is hydrogen fuel cell. And hydrogen energy give a high energy density we compare to other values like gasoline. And gasoline, we might be 3 times more weight of gasoline to give the same energy density compared to hydrogen. So this hydrogen how can be on the first choice. And the second thing we have to consider how to use it, because hydrogen has to be oxidized into water, and we need a catalyst. And the common catalyst is a platinum, and I shown here. But platinum is sensitive to carbon monoxide. It's usually contained in the normal gas like gasoline. Another thing is the cost. So think about this, how the fuel cell works. I will started the concept of a fuel cell. If this is a fuel cell device and there's a three things, layers, and on my right hand side is the anode part. This anode we can feed hydrogen in, and hydrogen will split at anode into proton and electrons. And at the cathode, we usually have oxygen in it. And after the proton is produced, it can transfer along the electrolytes and come to the cathode, and react with react with oxygen and to produce water. So water is the only production, so it is clean and it is no exhaust. So no other exhaust. Water is clean. So as you know, and what sort of fuel cells we can develop, and there are so many choices, and the configuration is usually similar. We have 3 layers at the sandwich, and in the middle is an electrolyte. At the side will be the 2 electrode, and here we show on the top is anode hydrogen, and on the bottom is the cathode. So anode, as I say, we fed hydrogen or other fuels in, and to produce hydrocarbon, to produce proton, and proton react with oxygen to produce water. So this is how it works. And fuel cells can be classified by the kind of electrolyte we used, and the electrolyte used determines the kind of chemical reactions that takes place, and or the temperature range we can operate. So by this, we got a few types of fuel cells. And the first one is proton exchange membrane fuel cells. It's usually work at low temperatures with a proton conductor as the electrolyte. And the reaction principle is the same as I shown, I've told there. And another is alkaline fuel cells. Or another 2 with phosphoric acid fuel cell and molten carbonate fuel cells. And I shown another color of solid oxide fuel cells to compare with other fuel cells. It's the temperature and the materials we use here. So I got another here showing the temperature of these few types of fuel cells work. For solid oxide fuel cells, it works at higher temperature, and it can give a better efficiency. And here I show is 50 to 60 is the normal value for efficiency. But if we combine with the cogeneration, it could be up to 80 to 90%. And for all the utilizations or applications, we can use for domestic power, or the small scale or even larger scale, and for even transportation. So a few examples for applications is some automakers use fuel cell car, and it can be shown here, and some other buses in North and South America and European and Asia and Australia use buses as well. So we are doing something in China at the moment. And train and planes and both can use fuel cells too. So I show a fuel cells car how it works. Usually at a stable speed, and the motor is powered by energy from the fuel cell. When the more power is needed, for example, during assembly, you want acceleration, the battery supplements the fuel's output to make it your speed, and similar to a petrol hybrid. So when you operate at a low speed, and when this low power is needed, so the vehicle run on battery mode. So this is how it works. If you want to get a high speed, and the motor functions as an electric generator to capture braking energy, so it's stored in the battery. So it works as a hybrid mode. A few more examples on the airplane using a fuel cell. So Boeing flies the first ever hydrogen fuel cells, and they climb up to 100 meters high sea level, and using a combination of lithium-ion battery power and a power generated by hydrogen fuel cells. So after reaching the altitude, so the battery can be disconnected, and the plane will fly straight and level at a cruising speed 100 kilometers per hour for about 20 minutes. So that's an experiment. And the commercial one is by the Craft. So the Airbus of the German Aerospace Center presented the first commercial airplane is containing fuel cells. It's shown in 2008. And the fuel cells, we say, cannot replace the jet engine, but it can work when to replace the power unit when the plane needs more energy, more demand. So this is showing a clean and easy, less emission. So what I'm doing now, so maybe the time limitation, I haven't shown other work. So but by some other new energies, we use we are doing some jet fuels, collaborating with South African. So if I have a chance next time, I'll show you some more work on there. And the principle of a solid oxide fuel cells is slightly different with other types of fuel cells because they use oxygen conductor as the electrolyte in the middle, the blue color as shown here. So at the anode, we use hydrogen as a fuel, and the cathode is still oxygen, but the action mechanism is slightly different. At the cathode, oxygen is reduced into oxygen ions, and the oxygen ions will transfer through the electrolyte and reach to the interface between the anode and the electrolyte and react with hydrogen and to produce water and electrons. So this is how the light can be lighted by this way. So we get current by this way. And of course, and water is only is exhaust if we use hydrogen as a fuel. There's a lot of advantage I've mentioned a little bit before, but I want to still show more advantage why we choose solid oxide fuel cells. Because the first thing is that no noble metal is needed, like platinum or gold. Is all no, we don't need this type of catalyst. Well, maybe some common compounds will be sufficient for the catalytic reaction. And the second advantage is the temperature we use is quite high enough to facilitate the extraction of hydrogen. And the third advantage is the high temperature fuel cells combine the heat and power. So this way we can go up to 80 to 90% of efficiency. And the fourth one is any kind of fuel cell. A fuel can be used a fuel of this type of solid oxide fuel cells like hydrogen, hydrocarbon. The hydrocarbon could be methane or other fuel gases. We don't need a lot of metal as the catalyst. And the fifth one is the no corrosion issue compared to other liquid or molten carbonate electrolyte fuel cells. And the seventh advantage is a clean and high efficiency system. So including other, we have less harmful gases emission. So this all there's advantage. And think about the fuel cells, how it works. We need three compositions, and the first one is anode, and the second one is cathode, and the third one is electrolyte. And for the anode, it could be a porous cement made with metallic nickel, and the YZ is a mixture. So the YZ is inhibit the sintering of the metal particles and prevent comparable thermal expansion efficient, and give oxygen ion conductivity, and nickel get electron conductivity. So how it works for the anode. And the cathode, we have some other choices. It's still perovskite materials like strontium doped lanthanum, magnetite. And electrolyte, we use truly a few choices like zirconia oxide or the cereal oxide. So here I'm going to talk about zirconia oxide because zirconia is a common used one. And for us able to get a good cell performance, is usually is our target to get a certain output. So we maybe have to design how the cell what is the cell's configuration. It could be the first one I show on the slide is electrolyte supported, or the fuel electrode supported, or could be the cathode, or we call the oxygen electrode supported. So this is a flat cells, or it could be a tubular cells. We have done some cells, this with the thin electrolyte and thick electrolyte, and I'll show you some my machine and instruments that we can do in our lab. And the first thing is we can use tip casting to do whatever size that you like. Could be big ones and could be cut into small ones, like show here is a circle one. It's quite thin. This is nickel YZ electrolyte as the anode. Or we can use a tubular cell mode to prepare tubular cells, or we can use a machine to press into the pellets to get the small flat cells. And this is some other machine for preparing slurry to make thin films, because in cells we usually need a good cell, means with low resistance, and the thin ones here are shown is a good one for fuel cell, and some other furnaces for sintering or calcination. We got some test machine like Celtron, two machine to combine to get the resistance test and the current density test, and some other big ones we can get into a higher current density values, and some gas tests if we really are interested in the gases from the outlet. So we've got some cells I'm showing here, like the circle ones here. The black one here is the cathode, and the green one underneath is the anode. That's a nickel color. If you know nickel, nickel is a green color if it's nickel oxide at that time. And when you use it, it will be reduced by hydrogen to be a gray color. And I've got some other machines for battery tests, some other work. And in able to get a good cell, we started to, for the target, is the performance. We care about the lifetime, the power output, and the efficiency. And how to get that is we started from materials. We have to choose a different electrolyte, a good electrode, or even what type of fuels you are going to use matters. And the structures and composition is some other thing, is always go through all the procedures. So I will show you some of my results. And for you to able to understand how the anode work, is the first requirement is a stable stability. It must be stable in all sorts of conditions. And here is mainly in fuel atmosphere, means hydrogen is feed in, is reducing atmospheres, must be stable in that condition. And the second requirement is the conductivity. It must be sufficiently high enough for electronic conductivity and oxygen ion conductivity. So for these two conductivity requirement, so we need either nickel to provide electronic conductivity, or YZ zirconia is an oxygen ion conductivity provider. And the third requirement is compatibility. So all the materials must be chemically compatible with each other. So otherwise, during the either the preparation procedure or the operation process, and the cell was either destroyed or just collapsed, it's quite hard to maintain for a long time. And the fourth one is the thermal expansion coefficient is understandable. So it must be have the same matching values for each composition. And for the anode, it must be porous, because we need all the gases to get through all the pores and get into the reaction site, meaning the interface between the anode and the electrolyte. So to ensure the fuel supplies is enough, and to remove all the reaction products, like if water is produced at the anode. So it's a combination between, you can't go high porosity, but high porosity, you have a less chance for connections. So there's always, you have to balance between the high values and the small values. For porosity, we usually get 20 is a good number, or 20 to 30, depends on what sort of fuels you use. And the sixth one is catalytic activity. The catalytic activities, anode materials must have good catalytic activity for all sorts of electrochemical oxidation reactions. So the anode must have good, strong ability to hold all the procedure, and with a low cost, of course, it's good, So that's all the requirement. So by that, according to this requirement, sorry, the sound is not right.
It's okay, Professor Chiron, we can hear.
Yeah, okay, I heard the sound. Yeah, and according to the requirement, and nickel YZ is a traditional anode, so it has good conductivity, can go up to 1,000 Siemens per centimeter, has an excellent catalytic activity towards also the fuels, methane, hydrogen, hydrocarbon, so even carbon monoxide. And carbon monoxide is a disaster in proton conductivity, proton electrolyte fuel cells. But here, it's not a problem at all. And at my right-hand side, we show a picture of a whole cell with nickel YZ as anode, and the electrolyte of YZ as the electrolyte, and the cathode is lanthanum strontium manganese. So yes, this is a good anode, but the only thing we have to face is some problem when this type of cell is operating. And the first is the nickel agglomeration. When it's because all the cells is working at quite high temperature, like 60 degrees, 600 degrees, or 800 degrees. So it come to be agglomerate over time. I mean, they lose their ability or capacity. So the second problem we have is the poor redox stability. And you can see a big gap between the cell. This is the nickel's problem. And the third problem, if we use hydrocarbon as a fuel, hydrocarbon is available on Earth. We don't need to do reforming or purification, but to get hydrogen. So from the cost of point of view, maybe we can reduce the whole cost for the fuel cells. So, but the carbon cooking is the main problem of nickel YZ electrolyte. This is why we think maybe there are any choices, and perovskite came out with ABO3 structures on my left-hand side. And these structures give us a lot of good oxygen mixes, means a good catalytic activity. We started work quite early, and it's not these materials are not new. You know, ABO3 structures. Maybe everybody, if they work on it, to know these materials, then even have done a lot of work on it. We are not the first, but we have done a few things. We find this materials has really good connectivity. I've shown here it's up to 1,000 Siemens per centimeter. But the poor thing is, so another good thing is it has high tolerance of sulfur. But the poor thing is it gives always low resistance, means, low polarization activity, means give this cells not a good catalyst. So we have to try to remove, to improve. And the first thing we'll think about the whole structure will be, we have a ABO3, and it's quite flexible. And for A side, we can use all sorts of ions like lanthanum, strontium, and for B side, we can choose titanate and nickel. And so for this variability, and we can use nickel to dope at the B side, and in the future, because we find a way to make it exsolve at the nanoparticle, so we give a better catalytic activity. But in the beginning, we didn't know. We just make a stoichiometric material, and with alpha here, I shows alpha means 1, means there's no, it is stoichiometry. There's no change on this value. I kept on 1, but it's difficult to get a pure faces. We tried different compositions with different lanthanum content, like I've shown here. It's all impurities. So it's not good to be used. So we think maybe there's a way. We try to use A-side deficiency. From the above, we change the efficiency value from 0 to increase to 0.03, increase to 0.08, and even 0.05 for the final chosen value. We find we easily to get pure lanthanum, strontium, titanate, nickel oxide. So it's a good news, isn't it? We found when the low lithium content, like this one on the, was shown on red color, red line, this S3 results, low lanthanum content give a low, we only need a small A-side deficiency value, like 0.03 will be enough to get a pure titanate. But if you increase the lanthanum content, like 30%, and here's black one, 80%, means we really need a high value of A-side deficiency. So this means, you know, you can tailor the deficiency to get the desired material. We're showing here as different value. You increase a bit and to get pure materials, and the density of these materials could be different too. When 10% of here's lanthanum is doped. Sorry, I changed the expression. It's a strontium, 10% of strontium, and it's when the deficiency is alpha is equal 0.05, you can get a dense sample, because you know all the sintering temperatures matters for the following procedure to prepare a cell. And if we increase the percentage of strontium and the alpha value increase a bit to get a denser sample, we test these 4 types of different strontium content. It's easier if the strontium content is higher. You see, we can get quite dense materials at quite low temperature, mean 1400, where maybe it's a normal temperature to prepare a whole cell, because we usually, if no matter it's electrolyte supported or electrode supported, we often have to go high to enough to make sure we can get a dense electrolyte to get a good cell. And another thing, the conductivity, we have got a good conductivity here. You see, it's for the 10% and 20% and 30 and 40%, we always get from a few hundreds Siemens per centimeter to 1,000 centimeter. So it's a good enough value for solid oxide fuel cells anode. So compare with the reported values, our work at the right hand beside is quite high. It's a few hundred at 800. We compare the 800 because this is a common temperature we use for the cells operation. And for the potential use fuel cells materials, we test the catalytic activity towards hydrogen. So it seems it's a good catalyst for hydrogen. And we also investigated the compatibility of this titanate with common electrolyte zirconium. Seems it has a good compatibility. There's no reactions up to 1,200 degrees for 10 hours. We also tested for 1,000 degrees for 30 hours. So it also gave a good stability. So no any reactions between our materials with the common electrolyte. So it is good. And we say why they have a really good conductivity. So we test the image. We find the nickel exhaust on top of the main bulk titanium. So we see a bit nickel growing up on top or even on the surface of this particle. So this sort of thing shown on the image we shown at here on the left-hand side. This is all nickels. So nickel give a good catalyst. It's not only in the letters, but by the reduction operation. So it's on the surface of the particle. So it gives a good catalytic activity. And after that, we assembled a cell with this anode and the electrolyte as a composite anode, and with the normal zirconium as an electrolyte, and another composition cathode of lanthanum strontium magnet with YZ. So it gave a good sign of what we have done is to change the deficiency. So a few this non-stoichiometry design give us a better cell performance, like shown on the blue line here. So it's a smaller polarization resistance and higher power density. So for all the materials, if we change the lanthanum content on the right-hand side, is 2. So always give a good power density and a smaller resistance if you use the deficiency. So it is quite good. So that's my anode section. And another thing we have done is on the cathode, because cathode has a similar requirement, like the stability. You must be, the materials must be stable in an oxidating atmosphere and must be conductive enough for them to able to move all the electrons and oxygen ions, etc., etc. And the third is, of course, the catalytic activity is similar to the anode, and other requirements is even the same, compatibility and the thermal expansion coefficient and the porosity. So it's also similar. I will not repeat it here again. And according to this requirement, we need to think about how this whole cell works. And first is the temperature. And it seems there's a trend now to reduce the working temperature from 900 to 1,000 degree down to 600 or even 800 degree for medium temperature, we call. By reducing the temperature, we have a wider choice for materials. We can have a better durability and extended application. But when you reduce the temperature, and the cathode could have some problem like sluggish reduction and oxidation problems, and also the polarization resistance, of course, will increase because all these materials work well on high temperature and at certain temperatures. If you reduce the temperature, means the activity will be reduced too. So, and of course, you cannot get a good cell performance. A nano cell is a choice. So one of them is nanofiber. We have gone through a few materials we can choose for all sort of cathode materials. It's all based on the perovskite AbO3 structure. So either it can be lanthanum strontium magnets, and these materials usually used for high temperature. Another good choice is lanthanum strontium cobalt iron, and this is for medium temperature. But if we prepare a good powder and things, and it can be used for quite low temperatures, like other two materials, barium, strontium, cobalt, iron. So all sort of designs can be used. So for barium one, it's a bit risk to be oxidized in carbon dioxide. It's easily to react with it to produce barium carbonate. So sometimes it's good to get a good cathode, but sometimes it's a risk to for a long-term condition. So we choose lanthanum strontium cobalt iron as a cathode, and to see if we can prepare some nanofiber. So we use this electrospinning machine to spin our solution, and on top of this collector. So after that, we got some porous nanofiber, and with a lot of continuous pores, and it's a good thing. And as reported in the literature, so these two materials, lanthanum strontium manganese and lanthanum strontium cobalt iron, these two materials can be used high temperatures for the first one, and the later one is for 650 degrees. So it's a good choice that we have done. After I've done a lot of research on the solvent, because the solvent does matter what you can get. Sometimes you cannot even get a nanofiber at all if you don't have a good solvent. And the viscosity they find is also changed if you add some nitrate in. So we've done these parameters on the viscosity, and to test the conductivity of the solvent, and to test the concentration of the whole solution. We investigate all the voltage we add and all the flow rate we spread on the collector. So after done all this research of this electrospinning, we've got good nanofibers. And these nanofibers, the first left-hand side one is the original one, just get it from the collector. And usually, for the cathode materials, we have to do all sorts of treatment at different temperatures. And temperature we've had done is 800 degrees C for the right-hand yield, and the left-hand side above is 850 degrees C, and we've done 900 degrees C. Seems these two, 800 degrees C and 850 degrees C, is a good calcination temperature. But go above to 900 degrees C, you lose all the structures. So means maybe you lose all the benefit we've got from the nanofiber. But they all pure lanthanum strontium cobalt iron. So it's give a good catalysis. And come to the cells, we have been done on some gas fuel cells and the solid fuel cells. How much time I've got, Chamin? I'm running off the time.
No, it's okay. Another 10 more minutes.
Yeah, I'll try to be quick. So biogas fuel is a normal. It's a mixture of 60% and to 70% methane and some carbon dioxide. So it can be used fuel in solid oxide fuel cells. And in these fuel cells, we have a risk of contain some sulfur. And this sulfur, we have to think how to use it, because it could be damaged to the cell. And we designed a cell with a similar structure with the dense electrolytes and porous anode and cathode. So we really get a good cell performance in also to fuse biogas and even hydrogen. So it's up to 2 watts per centimeter. And by that, we think about how these cells react in biogas, why it can give a good cell performance, because, you know, this is nickel cell. Nickel cells usually is not happy with sulfur. We tested and seems the cell is protected by the infiltration of a proton conductor that we have used in this cell. And we also done some the research on the reaction mechanism, and this can be either consume of hydrogen or at high temperature, high current densities is consume both hydrogen and carbon monoxide. So this we've got, if you know, we really get a good cell, and then and carbon monoxide is one of the fuel. So this we've got from this cell, we learned from there. And the durability is good in sulfur. It's by 20 hours and even more than that, it's get some degradation. You can see the line drop a bit for every hour, and here it's recovered so quick if we remove the sulfur from it, and it's even recovered to, it's better than even than the original value. And I've seen on the picture B. And we tested the SEM, seeing there's no carbon cooking on the SEM picture. And this biogas fuel cells, we have done some direct carbon fuel cells. In fact, I spent a lot of years on direct carbon fuel cells. Why we choose carbon fuel cells, there's a story. In fact, you usually think if this reaction, carbon is oxidized by oxygen, it's easy to carbon dioxide. This chemical reaction is easy, and we got so many benefits, like 100% efficiency and 100% of fuel utilization, and we also get high energy density, etc., etc. But we except from I'll escape from this because I'm running out of time, but we were not successful with carbon fuel cells in the early days, like in 1896, and the temperature worked as 400 to 50 degrees with molten sodium electrolyte, because this carbonate built up and the cell just collapsed very quickly. We think about maybe we can use oxide. Oxide is a solid, so it's, it's combustion. So it's strong enough for the cells working longer. And they try to work it out because the reaction for carbon to be oxidized is very hard. So they try to use the flow diet bed, or they try to use the Baudoir reaction to help the reaction, and even use some molten metal, but it's not really successful. So we got to some early ideas of direct carbon fuel cells is molten carbonate fuel cells combined with the solid oxide fuel cells. So we combine these two cells together to think about use both advantage, and some molten carbonate can have less chlorine problems. We use the solid, so there's no carbon dioxide recycle problems, and we tried a few carbon or biomass resources like pyrolyzed tire and some charcoal and wood chips and even some carbon containing fibers. So we were really successful to get something. And before I move to the good results, I would like to show you some unsuccessful results and how we understand the carbon can be used as fuel in the solid oxide fuel cells. And the first thing is the open circuit voltage is very low. If you don't have carbonate, it's 0.7 something, the value is quite low. But by adding 20% of carbonate, and open circuit voltage can go up to 1.1. It's even higher than the theoretical value. This is how we've learned from that. it's with carbonate, and the reaction could be, sorry, without the carbonate, and reaction could only be carbon is oxidized by oxygen ions and to produce carbon dioxide and then electricity. With carbonate, and the carbonate reacts with carbon either to produce carbon dioxide or carbon monoxide. This is how we benefit from carbonate. Another thing is, we've done a bit of research on the interface reactions I've done before, because I'm very interested in what happened there. So we usually think for the fuel cells and the reactions is only happen and showing here. I mean, the gas cell is very narrow zone from here to there, micrometers. But the solid oxide fuel cells can extend the reaction area from the narrow place into a 3D zone. So we've done the research to move the wire and to able to learn how this reaction happened. It seems if we move the wire and the ohmic resistance of the cell means all the contact and the cell itself, the resistance doesn't change because it's in the same value. Sorry, the polarization resistance doesn't change, but the ohmic resistance from the black line to the red line and then to the green line changes, increase a bit. So this is only the contact issue. It's not the reaction issue. So we've learned it's the whole reactions extend from 2D and to 3Ds. So this is why we've been quite successful. We've got good cells with this direct carbon fuel cells. It's almost to compare to the hydrogen fuel cells. This how I've got for the moment. So I think that's almost all I've got for now. So I've done some research on the materials on the whole fuel cells. So by now I've done a few things, a few publications on the materials and cells and carbon utilizations. And so I hope I've got something that you are interested in. And finally is acknowledgement to all my collaborators and all my funding support. So thank you for your listening. So did I catch up at a good time?
Yes, thank you, Professor Kaira. Ladies and gentlemen, we have now come to the Q&A session. Do you have any questions to ask?
Yeah.
You can either ask or you can put your question in the chat box.
So
please use raise hand option on Zoom if you have any question.
So I'm not used to Zoom yet because I usually use Teams. It's not allowed to use Zoom in China. So it's some new messages.
Any questions?
Hello, can you hear me?
Yes.
So as you mentioned earlier, you mentioned that the fuel cells are not enough to power jet engines. So what is the limiting factor? Is it the energy density of the fuel cells?
It's not really. I think the lifetime, and compared to the thing we use for the battery, lithium batteries, we now for fuel cells and the maximum maybe 30 hours or something. It's not long enough. Especially we have the problem like technology and the material issues, and nickel. As I mentioned, it's a good catalyst and anode, but it's still facing the lifetime issue. So this is why it seems it's a challenge to use fuel cells to power all sorts of transportation or cars or boats and even airplanes. So we're still on the road. There's a lot of things we need to do before it's come really to be an industrial market. So it's a challenge, you know. We've been doing fuel cells it's not new, but it's something we really need to do for like how to make a good materials for a start, and then how to make the whole fuel cells. I've been working on fuel cells as how many years? Let me count. I think it's 20 years, even more than 20 years already. So I'm still thinking maybe we still need another 10 or 20 years for it come to be true, you know, to be in industrial market. Did I answer your question?
Yes, thank you so much. And a small question again. So we use hydrogen as a raw material. So how do we produce hydrogen and the energy requirement to produce hydrogen?
Yes, that's a good question. So to come to the topic, so this is why my topic, I've thought a lot. Shall I bring you? This is why I didn't talk a lot about hydrogen fuel cells, and I focus on biogas and carbon fuel cells, because if you want to use hydrogen, and hydrogen there's a few sources. First, we get hydrocarbon from the earth, and then get reforming and purified to get hydrogen, or we can use the electrolysis to get from water, you know, electrolyze water into hydrogen. So all these procedures, you know, is cost money. And so hydrogen, we don't have pure hydrogen anyway. So we have to get hydrogen first. That's why hydrogen is popular, but we have to think about the cost. Compared to the cost, we cannot compete with lithium batteries. That's why this market is big, but seems it's hard to step in. Yeah, so.
Yes. Thank you for your response.
Thank you.
Any other questions?
Welcome for discussion comments, you know. It's
this is a good opportunity for you to clarify some doubts.
Yeah.
Similar question from that student asked. Just asking, what are the main economical barriers apart from the hydrogen production? What are the other economical barriers to large scale development of SOFC? I know that hydrogen production also not cost effective, but what are the other economical barriers to large scale development of SOFC?
Yeah, there's some choices like for hydrogen, you know, we if we can do better on the water from the sea, as I know some people in China, they quite successful to get hydrogen from seawater. So they've been trying work hard to get seawater to hydrogen. So maybe that's one of the choice, and to break up the wall, you know. So that's maybe a choice that I mentioned. Another thing is hydrogen is the density, you know, and the transportation, and also storage and the safety. So all sorts of things we have to consider. We not by the moment we haven't find. Yes, of course, transportation, we use a big cylinder and to carry it from one place into another. Also, we haven't found maybe a solid materials to store hydrogen to be safe enough for all the public to use. So transportation and safety. So there's quite a lot of things to consider. And for the hydrogen, so I think this is a barrier for hydrogen to be used. So I hope I have touched a bit of.
Any other questions?
Yeah.
Okay, silent indicates that no any further questions. Anyway, thank you, Professor Cairo.
Yeah.
So we will,
Thank you very much.
so
Yeah.
we will wind up the session now.
Yeah.
Our sincere thanks to Professor Kairon Jian for her clear and insightful session on SOFC energy conversions. Your presentation was both inspiring and informative. We look forward to working with you in the future as well. I also would like to thank participants for your active engagement. Your thoughtful questions and contribution made this session better. This workshop is one of the main interesting sessions planned for ICIT 2025. I encourage you all to join the main conference session tomorrow, November the 27th. There you will have more about new research, innovations from our 16 special tracks. Please ensure you have registered using QR code and link shared earlier. Participation certificate will be shared within 3 days for everyone who have registered. Once again, thank you for joining us today. We look forward to seeing you at the upcoming conference session. Have a wonderful day and enjoy ICIT 2025. Thank you very much.
Thank you for listening.